Alright, welcome. In this video, I want to take a look at our first greedy algorithm, and we're gonna apply that to a sort of a toy problem. It's a fairly simple problem related to overdue library books that I've just sort of created for this purpose. But the main purpose is to use that problem to study our new technique, which is greedy algorithms. So let's take a look at that first. So just to warm up here, when we get started, let's take a look at what a greedy algorithm is. So a greedy algorithm on its surface is greedy, and that's sort of where it gets its name. And what that means is that when making a particular choice, usually a local choice in the problem, we're going to try and be greedy about that local choice in some way. And that usually means making what we'll call a locally optimal selection or a locally optimal choice. We sometimes call this the greedy choice. And if our problem is one where greedy algorithm is going to work, then it has what we call the greedy choice property, where making that locally optimal choice, that locally greedy choice, will actually turn out to lead to the globally optimal solution, meaning the optimum that we're looking for. So usually these are applied in optimization problems. And in a few of our previous videos, we've looked at optimization problems in the context of dynamic programming. And at least, very shortly, we sort of took little stops there along the way to consider, well, could we apply a greedy algorithm to this problem? So when we were doing that, we were sort of considering, well, is there a greedy choice property for this problem? And so we can think of the greedy choice property in the same way that we think of other properties of problems, like optimal substructure. If a problem has optimal substructure, we can do divide and conquer, or we can do dynamic programming. If a problem has or if it has a greedy choice property, then we can do some greedy algorithms with it. And these properties sort of line up in the same way. They help us design algorithms. So when you're sitting down, again, imagine maybe you're facing a problem for the first time. You're not really sure which of these techniques or tools we should apply. Well, this is the property that we're going to be looking for if we want to apply our greedy algorithm technique. Okay, so this is the idea of a greedy choice property. This is sort of a way of reducing the problem to the sub-problem, although it's almost simpler in some ways. So we're not actually going to use self-reductions in this portion in the same way we did in divide and conquer and dynamic programming. That's because the self-reduction in this case would be very simple, not even worth writing down. In fact, most of the algorithms we're going to come up with in this section and this series of videos are all going to be ones that we could probably describe in a sentence or maybe two. And usually we're going to do that. We might not even write them in pseudocode in that case. A few of them we might write in pseudocode if they get a little more complicated than a couple sentences. But if we can express the whole algorithm in a sentence or two, remember, algorithms are intended to be expressed to other human beings. So usually a sentence or two is probably the most concise way to convey the algorithm. Okay, and we'll see that in a second when we get to our first one. The other thing that's going to be important and sort of critical here is that in greedy algorithms, when we make a choice to say work a day or not work a day, something like that, we're never going to revisit that choice and come back and change that choice. If we choose to work this day or choose this element of the subproblem, then that element is forever chosen. And that's really what the greedy choice property is telling us, is that making that locally optimal choice does lead to the globally optimal solution, so we don't ever have to reconsider it. Now I'm bringing this up because the technique we were just looking at, dynamic programming, it gets its name, dynamic programming, from the sense that it does this. It reconsiders every choice it makes every time a new piece of information would come in. So let's just think simply about the job selection problem. As the job selection problem, as the algorithm computes, we always grab one new day of information, and that new day, that new piece of information might change all the days we might want to work beforehand. So before we have that piece of information, we've decided which days we want to work, then that new piece of information comes in and that changes everything. That's the dynamic part of dynamic programming, is the solution changing as every new piece of information comes in. In greedy algorithms, the solution is fixed. Once we make a choice to work a day or whatever the subproblem demands, that's sort of written in stone, and we'll never reconsider that as we go. So that's one of the key differences. It's also why greedy algorithms are simpler, because once we make a choice, we're done. We don't have to, we add it to our solution and we move on. Okay, so what is the focus then in greedy algorithms? Well, if the algorithm itself is fairly simple, maybe it can be expressed in a single sentence, then the design part is not really as critical. However, because they're easy to design, you can come up with a number of different possible greedy algorithms, and some of them are usually going to be successful, and others of them might not be successful. And so, not in this video, but probably in the next video, we're going to try and explore that in a lot of detail. Now what that means is sometimes we have a greedy algorithm that is correct, and sometimes we have one that is incorrect, and we want to be able to tell the difference between them. So that's really the focus of what we're going to be looking at when we talk about greedy algorithms. So if the algorithm is actually incorrect, and we have in previous videos looked at a few incorrect greedy algorithms, and the way we showed they were incorrect was by coming up with a counterexample. This is, in a lot of cases, this is the easier case. If the algorithm is actually incorrect, all we need to come up with is an instance of the problem and show that it is incorrect on that instance. Meaning, usually we're talking about an optimization problem, meaning here we have an input where we know the optimal output is some value, then we run our greedy algorithm on it and show that it does not give us the optimal value. Now usually we can construct these counterexamples by hand. They're as simple as that, and usually they only take 2 or 3 pieces of input, whatever our input is, days we work or something we're selecting. We usually only need a handful of those at most to come up with a good counterexample. So sometimes coming up with counterexamples are easier. If we know the algorithm is incorrect, then we can just focus on that. Now remember, most of the time when we've got an algorithm in front of us, we don't know if it's correct or not. And so we're sort of doing two-pronged attack. On the one hand, we're trying to find this counterexample, maybe it's incorrect. But on the other hand, maybe it's correct. And if it's correct, we'll never find a counterexample. That's impossible. So that means we should be able to prove it's correct. That is, come up with a sequence of an argument, sequence of propositions that's going to argue for us that it is actually correct. And the way we're going to do that is using actually a fairly complex proof structure that really brings together a number of different kinds of proof technique. One I mentioned here is induction. We will also rest on proof by contradiction, and we're going to be doing sort of exhaustive proofs in the sense that we're going to be going through a number of cases in a lot of our proofs. So really, if you've had a chance to study mathematical proofs in a discrete math sort of context before, well, we're going to take all of those skills together and try and blend them into the types of proof. The sort of more rigorous mathematical proofs that we're interested in rely on all those different techniques as well as different branches of mathematics to bring all of that information together. So that's what we're going to see as we take a look at our first couple proofs of correctness. And again, in this video, we'll take a look at our first one. So I mentioned the problem that I wanted to explore here is the library book problem. It's sort of a toy problem, and well, let's just take a look at an example here, or at least the description here. So informally here it says, okay, let's say we're studying for our algorithms exam, and we've taken some books out of the library. Here it says we've taken N books out of the library. Maybe due to poor planning, we didn't read all the books and now they've become overdue. We still want to read all the books, but they're all overdue. We've come up with a strategy. Our strategy is, well, we're going to read a book and then we'll return it, and then we'll read another book and we'll return it, and we want to minimize the cost that this is going to end up costing us. And for simplicity, we're being charged $1 a day per book. So while we're reading the books, if we have N books, right out the bat, we're paying N dollars a day. But after we return the first book, we reduce the cost to N-1 and so on. So basically we want to know what order we should read the books in, so that we minimize the cost. Now, in order to help us do that, you've gone ahead and we've sort of determined how long it's going to take you to read the book. So, I don't know what that process is, but we'll imagine we've sort of gone through a process of, looking at the number of pages in the book, how many pictures there are in it, and so on, and coming up with an estimate of how many days it's going to take to read each book. All right, so now that you've got an estimate of all of the days, we want to come up with, an algorithm ultimately, but we know that the first step in coming up with an algorithm has to be formalizing that problem, making that problem as precise and concisely expressed using the language of mathematics. So say we want to formalize our library book problem. Let's just start with our input condition. What is our input here? Well, we've got library books, and here again, if we're a little bit informal or we're not thinking as precise and concisely as possible, we might start saying, hey, there's a set of library books, blah, blah, blah. But what is the important thing about the library book? What is relevant about the library book to us? Is it the number of pages? How many pictures? No, we already took all that information and we came up with an estimate of how long it's going to take to read that book. So maybe I'm going to set that up here, and I'm going to say, let's say I got some T's for times, not B's for books, because it's the time that is relevant to me. The times it takes to read the N books. Okay, so let's go to the output then. Well, what is the output? Now, if we look at the problem statement, it says we want to determine the order that we should read the books. And when we start talking about the order of things, what we're talking about is permutation. So I'm going to say the output here. Now let's be careful. This library book problem is going to be an optimization problem, right? Meaning we're looking for what? The minimum in this case. So usually our optimization problems, remember we've done this in a couple previous problems, optimization problems have usually two components to the output. One of them is the optimum. So I usually start there. We don't have to, but usually we start there. I'm going to say here maybe M, the minimum cost, but then what we really want to know is the order. So I'm going to say and T prime, and here's where I'm going to rely on some mathematical language for my precision. I'm going to say T prime is a permutation. Okay, so I'm going to say T prime rather is a permutation of T that achieves the minimum M. Now here I'm being a little bit vague. What do you mean achieves the minimum M? And we could actually go into a little bit more detail about that. But that's sort of going to be the next thing that I want to ask ourselves. So I've got a fairly similar expression here. I think I just reordered them a little bit to save myself a little space. But the question that I want to ask is, say we have this particular input here. So the input that I've set up here is got 6 books here. For convenience, they're all unique reading times, although I didn't say that was part of my input here. What would I have? 5, 2, 4, 3, and 6. Okay, so say we have this book. Oops, did I miss one? Yes, a 1. I squeezed a 1 in there. Okay. So say we have this ordering of these books, and it takes us these many days, 5 days, 2 days, 4 days, 1 day, and so on, to read each book. Think for yourself, hopefully already your intuition, this should not be a very hard problem to think about. What order should we put them in? The first question though that I'm going to ask here is, say we just read them in this order. Maybe we didn't want to think too hard. Maybe we hadn't studied algorithms yet. We didn't realize there would be a better order. So we just start reading them in this order. So the question I've asked is, what is the cost in this order? And the reason I'm doing that, asking that question is, can we flesh out a little bit what we mean here by achieves the minimum? Can we say that more precisely? There probably is a way. This is, a perfectly fine expression of the problem, but if we could be more precise, that might help us, say, come up with an algorithm. Okay, so let's say we were going to read them in this order. Well, we can see here 1, 2, 3, 4, 5, 6. There are 6 books here, okay, which means to start out, while we're reading the first book, we're being charged $6 per day, and there are 5 days. So maybe scratch notes. I got a 30 here. Okay, $30 for reading the first book. The next book is of length 2, but we're only being charged $5 per day now that we've returned the first one. So it looks like we got a 10. Okay, so let's keep going. So the next one, we got $4 per day times 4. That gives us 16. Next up, okay, the next is our 1. Well, that one we're being charged $3 per day, and that one's only 1 day to take. So that's 3. Then we're on to $2 a day, and that one takes 3 days to read, so I guess that's 6. And then the last one, well, we're only on $1 per day then, and that's a length 6, so that's also 6. So adding these all up, what do we got here? We got 40, looks like 56, 59, 65, 70, oop, that was supposed to be a 1, let's make that a 1, $71. Okay, came up with the same math, $71 here. So the question then is, can we express the total cost of our solution? Say we just go general now, instead of, now the steps that we're doing here, and this is going to be important for us, is remember, this is an instance, but up here we're calling it an input, and the difference between an input and an instance is an input is general and an instance is specific. And so we've just calculated the cost for an instance, but we want to, if we want to express this a little bit better, we want to come up with a expression for the input, the general case. So let's see if we can do that. Now, one thing we're going to notice here is, what do we have? We have a sum. Okay, we have a sum. And for the moment, let's say we have n books, so let's just simply say I equals 1 to n. Now, we just wrote it in such a way where what we were multiplying by, and I'm leaving myself some space here on purpose, is t of I. So right, t of I, t of 1 was 5, t of 2 was 2, 4, 1, 3, and 6. But this was in the order they gave it to us. And we don't want it in the order they gave it to us. We want it in the order we're going to output it. So I'm going to put my t prime on there. So the output is going to give us the cost. Now the other term we had here was this dollar term, and we notice it's reducing down. And in fact, it started at 6, which was in this case n. So the first value that it is n minus 1, n minus 2, all the way down to 1. We notice if we write that up that way, that's just 1 to n, but we're getting it in the reverse order. So we need to have an expression that writes it in the reverse order. Well, it's going to be an n minus something probably, right? Because we start at n and we go down. Now we'll notice if we just minus I, which is what we want to do, we're going to get n minus 1 to start out, so we actually need to do plus 1 more. N minus 1 plus 1 gives us n, the first value. N minus 2 plus 1 gives us n minus 1, the second value, and so on. Okay, so this formula here expresses the cost of a solution, a possible solution where t prime is the solution. And our goal is to minimize this cost. So we could have put that expression right up here in our definition if we wanted to. All right, and we've got that same expression here on the slides, but let's continue. And I want to continue focusing a little bit on this idea of an instance, but also our idea of solution. So we came up with a solution here. That's just reading the books in the order that they're given to us. But we've said here, imagine we get any solution t prime. Here's the way we could express the minimum cost. Okay, and again, hopefully you're already thinking to yourself, what order would I put them in to minimize cost? So again, let's take a closer look at this instance. So here I have an instance. Now here, I'm going to say, here I'm considering solutions to this instance, but at the moment I'm being very loose on what I mean a solution is. A solution here, I'm thinking just pretty much anything anyone could give us that they think is a solution. Now, some of these solutions we're going to reject out of hand, and others we might accept, but they might not be optimal. They might not be the best solution we want. So let's take a look at them a little bit closer. So the first solution I have here, S0, is the solution that we just looked at, them giving us, or us taking the books in the order that they were given to us. Okay. So again, I've kind of got a rough definition of what I mean by a solution here. I think I'm saying it's some ordering of books that's pretty loose, okay? But the first one matches that definition, and the second one matches that definition too. It's just reordered the books, at least the times. Here we're just looking at the time it takes to read the books. Now if we look at S2, it is an ordering of some books, but you'll notice it's missing some books. S3, also an ordering of books, but it's just a single book repeated over and over again. So it's missing books, but it's also repeating books. A couple problems there. And then the last solution, again, doesn't seem to have any of those problems. So the first definition that I want to apply here is the definition of validity. Okay. So a solution is valid if, at least according to our problem, it counts as what we might count an acceptable solution to the problem. Okay. Now what that means is, say you're out in the real world and you're facing this problem, you had to read the books, you didn't know what order to read them in. Well, as long as you read them in some order, that maybe satisfies what your needs are. Okay. Or in the real world, again, you know, you're trying to minimize the cost for, say, a trip, a road trip you're going on. Well, any plan to get the road trip completed would be a valid solution, even though the problem may be to find what we're going to call the optimal solution. So the optimal solution then, so again, maybe let's just look at our 5 solutions. S2 and S3 technically are what we're going to call not valid solutions. Okay, and how do we know if our solution is valid or not? Well, usually in our optimization problems, if we look at it, there's usually going to be two statements in there. One statement is going to be a statement about what validity is, and in our case the validity statement is this short one here, a permutation of t. S2 and S3 do not satisfy this condition. That means they're not valid. They're not even an acceptable solution. We don't read all the books, so they don't satisfy our constraint. On the other hand, here we have the second criteria is our criteria of optimality. So any old permutation of t is going to be a valid solution here. Any ordering of the books is a valid one, but we want the one out of that selection, out of that group, that's the optimal one. And we're presuming here that there's only one optimal case, although for many problems that's not the case. There might not be a single optimal solution. And in this problem, it depends on if we have unique reading times or not. If we have unique reading times, then there's going to be one unique solution. And we'll see this when we get to our proof. If we have ties, if this was our input, 6, 6, 6, all 6s, then it doesn't matter what order we read the books in, because each one takes 6 days to read. So again, think about that. And again, maybe that's going to inform us a little bit what order we want to put them in. Well, I've got a little spoilers here, I guess. The only valid solution here that is optimal is solution 4, the one that puts them in an increasing order. Okay. Not, say, solution 1 that puts them in decreasing order. Now, why is that so? Maybe you might notice if you, say someone came along, usually in CS we have sort of 2 partners that come along, Alice and Bob. They help us with a lot of our problems. So imagine our friends Alice and Bob come along and they say to us, hey, I think the optimal order is S1. well, it should be pretty easy for us to prove that's not optimal. And in fact, we probably don't even need such a large input. Okay, so again, imagine we have Alice and Bob saying to us that they think we should put it in decreasing order instead of increasing order. Can we come up with a set of times that we can prove that this doesn't work? Well, I'm just going to start out here for my input, and I'm going to make the absolute easiest input here, 1 and 2. I could do 1, 2, 3, 4, 5, 6 like we had before, but that just makes me have to do a little bit more extra work. Let's see if this one works. I think this one's going to work. This is the simplest possible input we could get, where we at least have more than one output. If we only get one book, there's only one ordering we could read them. But here, there's 2 possible orderings. We could read them in this order, 1 and then 2, or then 2 and then 1. So if we're really considering the counterexample here, first of all, the Alice and Bob's solution says put it in this one. We hopefully think we should put it in this order, so why don't we just go ahead and compute the cost? If we put it in this order, what's the cost? Well, while we're reading the book that is 1 day long, we're spending $2. And while we're reading the book that's 2 days long, we were spending $1. So that looks like it's 2 plus 2 is 4. What about this ordering? This ordering then, we're going to say, while I'm reading the book that takes 2 days, I'm spending $2, plus, while I'm spending $1 while I'm reading the book that takes 1 day. Well, that looks like that's 1 times 4. That's $5. Okay, it worked out. It might not have worked out for us, but I tried the simplest possible case to see if it would work out for us, and indeed it did. Okay, it shows here that Alice and Bob's solution, going down, going in decreasing order, is not the best case, and in fact, it's the worst case. We definitely don't want to read them in that way. That's how we spend the most money, not the least money. So so if that's the case, we just did a quick counterexample. Maybe we said to Alice and Bob, look, that one's not going to work. Well then, which one does work? Well, this increasing order one is the one that we want to consider. Let's just look a little bit closer at it, at the solution then. So the first thing I've got here is just sort of a comment. I'm not going to write pseudocode like this for a lot of my greedy algorithms, because it's kind of wasteful. It's almost too much effort put into such a simple algorithm. So the algorithm that I have here just says, say we're given the books in some random order T. What are we going to do? Sort them into ascending order of their reading time and then return that. Okay, so that's almost too much structure writing the pseudocode when we can write a very simple sentence here. I've got 3 different sentences. Read the books in ascending order of length. Always read the shortest book first. I like this one because this one highlights the greedy choice. Read the books from shortest to longest. All of these are just simple, natural language ways of expressing the algorithm. And sometimes, remember, the reason we want to use pseudocode instead of using actual code is because it allows us to bring in natural language constructs that we haven't built into actual programming languages yet. And so the same thing is here. If we can bring the natural language in to express our algorithm, then let's do that. That's the point. And so here we can actually eschew pseudocode altogether. We can get rid of the pseudocode and just express the algorithm as a simple sentence or 2. And usually this is how we're going to go. If the algorithm can be expressed in a sentence or 2, we'll do that. If it takes more than maybe 3 or 4 sentences I might make as my upper threshold, then looking like maybe you want to start putting it into some kind of pseudocode structure, especially if there's a non-obvious loop or recursive part that you want to highlight. Okay, so that's just meant to say that, as I push forward in the next series of videos, you might see some pseudocode here and there, but every once in a while we might completely skip over the pseudocode. You might say, are we overlooking that? Well, hopefully you can generate that pseudocode yourself very quickly, because it should be very simple. Okay, and most of the time, a lot of these greedy algorithms, we're going to be greedy in the sense that we're going to be picking the smallest thing or the largest thing or something like that, meaning a lot of these algorithms are merely sort it. And the whole algorithm comes down to sort something. Okay, and so I'm going to highlight this here, that obviously that's going to be maybe the biggest cost. We're going to sort it, then maybe we have to read over them if we're actually reading them, something like that. But to iterate over them as order n, that's going to be dominated by our sort operation. So in this problem, we can think of this as an n log n solution, because hidden in here, always read the shortest book first, doesn't read, can smuggle in the fact that that means we actually have to sort them. Okay, read the books in ascending order or from shortest to longest. Maybe those ones maybe make it a little clearer that we actually have to do a sort in there. Okay, although I like all these expressions. Okay, so as I mentioned here, we're still stuck with sort of the main task. Can we prove that this algorithm is correct? So to do that, that's the main task here. I want to use a proof of correctness. And the proof of correctness I'm going to use, as I mentioned already, is sort of going to be a blending of a number of different proof techniques. And if I really wanted to highlight every step of the proof, it's already going to be 2 slides long, but it would be sort of 3 slides long if I wanted to highlight every single step. So I'm going to be trying to show almost every step, because for most of us, I think this will be one of our first real proof of correctness we're going to look at. But if you go venturing out into the internet, especially if you start reading proof of correctness by people who study this formally, you might see they strip away a lot of the proof, sort of assuming you could fill in the details yourself, which is fine, because that's normally how math goes. We speak to our audience. If our audience are a bunch of elementary school students, we have to break it down into smaller base parts. If they're high school students, we have to describe it in a different way. If they're undergrad students, we assume a different understanding, and so on. And so a lot of papers that are written out there are assuming maybe a graduate level understanding. Well, I'm going to assume sort of an undergraduate level of understanding, so I'm going to fill in some more of those blanks, but that maybe in the series of videos as we go, I'll comment on why you might see some of this stuff not really included in other proofs you might see. Well, let's start with our first one. We're going to go step by step, so let's take our time. This problem is fairly simple, and the algorithm we came up with is actually fairly simple too. And so what that's allowed us to do actually here in the theorem is express the theorem very succinctly as one sentence. So let's just read the sentence. It says, always reading and returning the shortest book first will minimize the overdue cost. Okay. Now, there are some things in this sentence that are assumed. One thing we assume is, how do we calculate overdue costs? Well, that was built in the problem statement. So some of the things we assume that are already in the problem statement, we don't really need to restate them in our theorem. Okay. Also, sometimes, so you'll notice here this first bit, always reading and returning the shortest book first, that is a single clause describing how our algorithm works. Okay. Now, sometimes our algorithm is going to take more than one sentence to describe, or one clause as it does here. If it takes more than one sentence to describe, then that means we might want to break it out of our theorem here and write it above. We'll write something like algorithm 1, and we'll write out maybe a little pseudocode or a small paragraph description. And then down here, instead of saying how the algorithm works, we would just say something like algorithm 1 will minimize the overdue cost. And that allows us to sort of push the reference out of the theorem into some other part of the math that's going on around this theorem, usually the definitions up above. So in a very general sense, the theorem we're trying to prove is our algorithm is correct. Okay, let's translate that a little bit more. Our algorithm is correct for this problem. Now, the minimize the overdue cost bit, that clause is telling us what it means to be correct for the library book problem. Okay, so in this case, we've basically taken the sentence, our algorithm is correct for the library book problem, and we've filled in what that means. What is our algorithm? Always reading and returning the shortest book first. And what are the criteria for being correct for our algorithm? Well, returning the minimum cost. Okay. All right, so let's dive in. So one property of proofs that's going to be important is that our proof is general. We just did a counterexample where our counterexample proved that something didn't work, and in that case we just did a proof by example. Now most of the time proof by examples don't work. They happen to be helpful for trying to prove something false. That's what we just did for the counterexample, but they're not great for proving something's true. Okay, so proving our algorithm works for just one input, for instance, is not good enough. And then for that matter, proving that it works for 7 instances or some other handful of instances is not enough. We need to prove that it works for every input, and that means it's general. So we need to start out by saying that we want to start generally. So I begin most of my proofs here with this assumption. Assume our input is arbitrary, meaning it's not some specific instance that we've come up with. It's any instance we could come up with, any possible one. Okay. Now this word arbitrary, you've probably encountered it in some discrete math before, but I like to bring it up when I use it in my proofs, that sometimes we sort of think arbitrary means random, and it's a good way to think, honestly. It's a good sort of synonym to bring along if you need one. Sometimes arbitrary means sort of chosen at random, but when I'm using it in a proof, I like to think of it in a little bit stronger context, which is really what arbitrary means here. It means any, and so that's why random kind of works. It means pick anyone at random, but in our context, what it really means is imagine there's one of those random ones that's the worst one, the one that you really wish they weren't going to pick, the one that, say, your proof isn't going to work on. Well, that's the one they're picking then. So when we say here that pick an arbitrary one, we mean the trickiest one. Not the easy ones, not a random one even, but the trickiest one, the hardest one. And our proof should work for that one. Okay, so that's what we're going to do here. Okay, so starting off, general, arbitrary. All right. The next bit is, and I want you to think of your proof a little bit like a program, since a lot of you might be programmers. If we want to write a program, one of the first things we do is we start declaring the variables that we're going to be working with. Well, the same thing is true in a proof. We need to start defining the variables that we're going to be talking about. So we can't just jump in there assuming you know what x, y, and z are. We need to say what they are. So here I'm going to define S to be our solution, the solution that our algorithm returns. So again, given this input, we're going to sort our instances from shortest to longest, right? So let's let S be that. Let's be S be the list of books in increasing order of their reading time. That's, as I've got stated here, this is the order we would read and return the books. So this is an expression of our output. Okay. Now, our goal is to show that our output is optimal, and there's a couple different strategies on how we might want to do that. But the strategy that I'm going to use in my proofs is I'm going to compare S to an optimal solution, another solution that we already know is optimal. How do we know it's optimal? We're just going to assume it is. Okay, and so the idea behind this is that we know in the realm of all the solutions, all possible solutions, one of those solutions is the optimal solution. Now, at the moment in our proof, we don't know which one it is, but I'm going to give it a name. I'm going to call it O. Okay, so let O be the list of books in an order that minimizes the overdue cost. This obviously is what we might call an optimal solution, because that's the criteria for optimality in our problem. Now, my goal is I want to show that S and O are the same. And the rest of my proof is a strategy to try and tackle that. Okay, show that S and O are the same. Because if I can show that S and O are the same, then I've shown that S is optimal. Why I know O is optimal by assumption. If I can show S is the same of it, then S must be optimal. Now, there's going to be a little bit of a problem here, and some of us might be facing this already, which is intuitively we think, well, isn't this obvious? And that's the part that I'm trying to crack open for most of us, is we need to crack open that isn't it obvious feeling and say, why is it obvious? Why do we feel it's obvious? So if you feel like it's obvious, great, you're already there. You have that sense, right? If you don't feel it's obvious, well, great, then follow us along in this proof, because hopefully I'll convince you as we go. Okay, so again, we're still just setting up, we're just grabbing the pieces we want to talk about. We've got S, our solution, we've got O, an optimal solution, and we want to now compare the two to each other. Okay, so let's begin comparing them. Now, the other thing that I'm going to mention here is I've got them in two different orders. Now, often at this stage in our proof, we're going to want to line up our two solutions for comparison. Well, the way we're going to do that here is we're going to line them up by saying, which book did you read first? Okay, so we're choosing the shortest book. Which book did O read first, for instance? So I'm going to say, let's compare these two solutions one at a time, starting with this first book. Now, if we read the same book, then we agree. That's good. That's what I'm trying to argue. Now, let's just assume for the moment that we actually agree on every book along the way. If we do, then that means S is equal to O. That's what I was trying to argue. So let's back up a second. I said, assume they're the same. Then they're the same. Well, that's obvious, right? If we assume they're the same, then they're the same. So what that means is that branch of the proof, I don't really need to go down it. I've done it. It's easy. If they're already the same, if S is already equal to O, there's nothing to prove. I'm done. So the problem I need to face now arises when we say, okay, but let's assume that we're going down this list of books, and at some point we choose to read different books. Okay? S chooses one book, O chooses a different book. Okay? And again, a part of the definition part of my proof, where I'm just defining what I'm talking about, here I'm going to say, well, let SI and OI refer to the reading times of those two books, because that's what's really going to be important to us. Okay? So we're going down the list of books, and we get to book I. At some point at book I, we're going to read two different books. SI and OI refer to their reading time of those books. Okay. Now, I want to step forward on this, but I do want to take a pause to make just mention what's going on behind the scenes here. I said if I was going to write out every step of this proof, it would get pretty long. Well, I'm sort of smuggling under the carpet here a little bit of induction going on here. When I say let's assume at some point we read different books, okay, what I'm really doing here, this is where some induction's coming in. I'm saying assume up to this point that they were the same. Okay, and remember, that's that kind of inductive hypothesis feeling where we say, let's just assume up till here everything was okay, but now that we've got here, let's show that since it was okay up to here, it's still going to be okay at, say, point I, where we are right now. Okay, so we are doing induction here, but I'm not going to write the machinery for induction into this proof because it's just going to fill out more stuff. Okay, so we sort of smuggle that induction in here when we make this statement. Okay, let's assume at some point for some I that we differ. Okay, and you'll see this creeping into a lot of our proofs. Assume at some position we have a disagreement. So let's assume we've made a disagreement at this point. Again, SI is the reading time of our book. OI is the reading time of the optimal solutions book. And there's three possibilities relating these two values, only because these two values are numbers. The three possibilities I'm considering are our book could be less, the optimal book could be less, or they could be the same. Those are the only way that two numbers can be related to each other. One is greater than the other, or they're equal. So let's consider these cases one at a time, and I'm strategically tackling the cases in order of easy case to hard case. Okay, now I kind of have some mathematical experience, so I know which case is easy and which case is hard. If you were doing this on your own, say a little practice or as some homework, you might you might not know which case is easier and which one is hard. Well, how do you find out? You start doing them. And the one that you finished first is probably the easy one because it was the easy one. If you start tackling the case and it says, hey, this one's hard, try one of the other cases, okay, and see if it's easier. Okay, sometimes they're all hard, sometimes they're all easy. Okay, in this case, the first one's going to be the easiest one. Let's take a look at this one. This one, case 1. So remember, there's 3 cases. OI is less than SI, OI is equal, OI is greater, and we just need to handle each case. Okay, at this point, we're now branching into a type of proof called an exhaustive proof, a case-by-case proof. Okay, and we're doing that inside this induction that I smuggled in. Okay, so we're doing this case. OI is less than SI. These were the reading times of the 2 books. That means OI is shorter in its reading time than SI. Okay, now, wait a second. What does our algorithm do? It says always reading and returning the shortest book. So is it possible that OI is reading a shorter book than we are? Okay. So again, my statement here, in this case, it's selected a shorter book than we have. So this contradicts that we always select the shortest book. Okay, we always select the shortest book. There's actually one possible case where O could do this without contradicting us, which is if O reads a book that we've already read. So imagine we agreed up till now, we've been reading the shortest book up till now, but for some reason O goes back and rereads another book. That would be a contradiction too, because we assumed, let's see, we assumed up above here that O is an optimal solution. In particular, it's a list of books in some order. It's a permutation, meaning that's an impossibility as well. So what we're trying to do usually on the first couple easy cases here is rule out a few impossibilities. What do we know about our algorithm? What do we know about the optimal solution to rule out some cases? So this case is just impossible. We know that our solution always reads the shortest available book, so this case doesn't occur. This is a contradiction. On to the next case. All right, let's consider our next case. The next case I'm going to consider, next easiest, is what if they have the same reading time. Now here what we're talking about, in the instance we looked at before, I had unique reading times. Every book had a unique reading time. Well, that wasn't stipulated as a promise in our input, so it's possible that some of our books had the same reading time. And all we're encountering in this case here is we're saying that up above here where we just said let O be optimal, if there's actually a tie between some of our books, there's actually more than one optimal solution. So here, what the strategy we're going to take in our argument going on here is saying, oh, yes, we picked an optimal solution O out here, but we picked the wrong one. There was more than one optimal solution out there, and we wanted the one that agrees with us on our picks. So the argument I'm going to make here is what we're going to call a swap argument, okay, where I'm just going to do a little surgery on O. I'm going to say, look, so let's go through it. So let's say this. In this case, we have the same reading time. So now I'm going to do this surgery on O. I'm going to alter O by swapping our book is the one with reading time SI, with the book selected by O, the one with reading time OI. But because they're equal to each other, in our formula for the cost, okay, I'm getting ahead of myself. I'm going to call this new solution O prime. So after the surgery, I do the swap. Now I have a new solution. It's called O prime. Now, what's important is after we've done surgery to one of these solutions, we may have upset that it's no longer valid. We may have made it non-valid. For instance, one surgery we could do is just delete a book out. Well, that would make it invalid. Okay. So we now need to make sure that it's valid. So I'm going to say, note that after the swap, O prime is still valid because it still reads all the books. Doing a swap on a permutation leaves another permutation. It's still a permutation. So we haven't deleted any books, we haven't duplicated any books, we haven't missed out on anything. So we know we're still valid. That's point one. Point two is we want to argue it's still optimal. And that's where we're going to come in. Well, since the reading time of both our books are the same, that if we computed the cost of our two solutions, the cost would be the same. So if O had an optimal cost, then O prime must also have an optimal cost. So in the swap step of the argument, we're basically saying, look, we made a mistake when we selected O. We wanted to select the one that agreed with us. So if it disagreed with us, and it disagreed with us because the cost of our book or the time it takes to read our book is the same, we'll just fix that mistake by swapping it out. Swap out O for O prime. O prime is also optimal. It is also valid, and it also agrees with S at point I. Which means now, say point I was where we disagreed, now we're saying, now go to the next point I. This is where induction kicks in again and says, okay, go to the next point I where they disagree. If it was only these ties that we had to worry about, we'll just swap all the ties until we agree. So far, we know the first case is impossible. The second case, we can handle if we just do a swap. So now we need to handle the third case. And here's some foreshadowing. I said this proof's going to take 2 slides. Well, guess what? It's not going to fit all right here. Okay. So let's get started with case 3. So case 3, let's just immerse ourselves into case 3. What is case 3 saying? Well, case 3 is saying OI, the book that O selects, takes longer to read than our book. Okay. Now here's where I think some of us will want to say something like this. Well, then O's going to cost more than S, and that's a contradiction. And that's right. That's actually what this proof. The rest of this proof is. Therefore, O is going to cost more than S, and that's a contradiction of our assumption that O is optimal. That takes the minimum cost. Okay. However, the it's obvious card can be played in situations when it's not obvious. And it can also be played in situations when it's not even true. So the goal here of our proof is to fill in the it's obvious claim. We want to say it's obvious now that if O selects a longer book than we do, it's going to cost more money than we do. Well, can we prove that using math? That's the bit that we need to fill in here. Okay, and that's really the crux of this. All right. Now, so again, I'm gonna give us a strategy to prove it, because some of us might be thinking, well, it's obvious to my brain. The brain computer inside me thinks it's obvious, and because the way our brain handles things that are obvious is it tries to automate them. It doesn't make us think about it. We don't go back and justify to ourselves 1 + 1 is 2 every time we need to consider it. It's obvious, right? So it's sometimes hard to open up that can again and say, look inside and say, why do I believe this? Why do I think this is true? But let's do it. So to do it in math, again, sort of like in just normal programming, we need something to talk about. So if we want to talk about the cost of our 2 problems, really, and here I want to point out a subtlety. We want to talk about the cost of O and S, but that's sometimes hard, because we know that O and S agreed up till now. We made that assumption in our inductive bit up above. We assumed they agreed until we got to point I, but we don't know what's going on after point I. It could be all willy-nilly out there, all disagreements all the way, the rest of the way. And that's a lot to untangle. We only want to untangle this one disagreement right now. Okay, all the other disagreements should be handled by induction later on. Okay, so since we only want to focus on this disagreement, we're going to do the same strategy we just did in case 2. We're going to do a swap. But in this swap, we're doing the swap not to say that everything's fine at the end like we did up above here. We're doing the swap to say everything's not fine. Hopefully, contradiction. Okay, hopefully contradiction. So, again, if we want to do this, we want to talk about the cost. I need a definition of the cost. That's why earlier on, I went through that little exercise to say, can we express what the cost is going to be as a sum? So remember, we had this sum, we had this term, which was this is the dollars per day, and this is the how many days it is. And so I'm just going to say for O, we have these OIs, and for O prime, after we do the swap, we have O prime I's. Okay. Now what are we swapping again? Again, we're just swapping in O, the optimal solution, we're just swapping our book for O's book. So we're swapping SI and OI, if you will. Okay. So in this sum, somewhere SI appears and somewhere OI appears, and we're going to swap them out. Oh, I just noticed an index problem here. Let me fix the index problem on my slide. We got k's here. These should be k's as well. All right, with k's in there, okay. Now let me just, since that was a little error there, I want to just make sure that it's clear what the error was. Why did I switch from I to k? Well, we've already been talking about I. We've used I. We've defined it up above here. We have already said what SI and OI. So if I had left OI there, it was like I was using that same value OI over and over again in my sum. That's not what I meant. We want the different values as given out here. So one of these values of k between 1 and n is OI. And one of them is also SI. Okay. All right, let's continue. I want to look closer a little bit at these two functions. And in fact, what I want to do is we want to compare these two functions. We really want to know which one is bigger. Okay. And so maybe let me just take a quick aside here. Say we wanted to argue something like this: the cost of O is greater than the cost of O prime. This would give us a contradiction, because that's saying after we made a swap in the optimal solution, we got one with a smaller cost. Okay, so this is sort of what we're trying to argue. All right. Now, trying to argue this directly is a little bit hard, so we sort of do this indirectly by saying, look, if we do a little algebra and we minus this off on each side, we get this. If we can show the difference between the two costs, cost of the optimal solution minus the cost of the other solution after the swap, if we can show that that's positive, then that's equivalent to showing this, that our optimal solution is not optimal. So this is actually what we're going to try and prove here. So that's how I'm going to continue our proof here. Is let's look at the difference between our twos, cost of cost of O, and cost of O prime. And then the only other thing that I'm going to have to do here is we're going to have to make an assumption that that the optimal book reads our book. Remember, we're calling it SI in position J. So when we do the swap, OI, where it is right now, is in position I, swaps out with position J. That's where our book was. Okay, that just gives us, again, a label that we can use to express that index. All right, so again, all I've done in this step here is I've taken the definition we had on the previous slide for our CO and our CO prime, and I've just pulled those out. Now, what I want us to realize is that in these two sums, almost every term is the same except for the two we swapped out. Okay, and what that means is we're doing some term minus the same term. So luckily, all those terms cancel out and all become 0. So the only difference happens on the two values that we swapped out. So let's look at them. That's what I'm going at on the next line. So in O, we know that OI was at position K equals I. So I've subbed in I here for K. We also know, according to our assumption here, that SI was in position J. Okay, SI was in position J, so I've got SI in position J. Now, after the swap, that's our O prime, we just swapped those two positions. So SI becomes in position I, and OI becomes in position J. Okay, so all I've done is all the other terms cancel out of the sum, and we end up with these 4 terms that don't cancel out. And we want to know what happens to them. Okay, so the next thing I'm going to do is I'm going to try and factor out you notice we have 2 terms with the n minus I plus 1, n minus I plus 1. So we factor those ones out. And then we've also got 2 terms with the n minus j plus 1 and n minus j plus 1, and we factor those 2 out. And let's do the first one. We get OI minus SI. And then the other case, we get SI minus OI. So I've just factored those into these two terms on the next line here. n minus I plus 1 with our OI minus SI, and then same thing, our n minus j plus 1 with our SI minus OI. Now, the next step is just noting that we can actually factor a minus 1 out of here. If you factor a minus 1 out of the minus like this, it just reverses the order. We get OI minus SI. The reason we want to do that is to put it in the same order as before. Okay, so now I've factored the minus 1 out, and it ends up turning this plus to a minus. Okay, but it allows me to reverse the order here. Why? Now those two terms are the same, and we can factor them out, and that gives us this weird thing. We get our n minus I plus 1 minus our n minus j plus 1. Okay, this whole term OI minus SI we factored out. Okay, last step. All this is just little algebra. Okay, nothing really fancy going on here, but our last step, we're just going to, again, finish some algebra to simplify. N minus n, we're going to get 1 minus 1. Okay, and we're going to get minus I minus a minus j. That just flips it around. J minus I. Okay, and once we get to this step, remember, all we were trying to argue that this is positive. Well, this is positive because, 1, j is greater than I, so this is positive. And we assumed at the beginning of our case, so on the last slide, that OI is greater than SI. That's the case we're in. So because of this, the cost must have increased, or another way of saying that, rather, the cost of O should be greater than the cost of O prime after we made this swap. Now remember, this must be a contradiction then. Now we said this earlier, it's obvious that the optimal solution then would cost more. Well, it may not have been obvious to you before, but if it's not, it should be obvious to you now. This math helps us argue that. Okay, so this means in our last case, because this is positive, that the cost of O is greater than the cost of O prime, and this was our contradiction, our assumption that O was an optimal solution. If it was optimal, it should have the minimum cost. If we can find a solution that has less cost, that's a contradiction. Okay. So of our 3 cases, 2 of them reach contradictions. So that means those cases are impossible. So the case where O selects a shorter book than us is impossible because we always select the shortest book. The case where O selects a longer book than us is impossible because that would increase the cost. That's what our math does here. So both of those cases are impossible. So the only case where it could disagree with us would be case 2, and that was the case of a tie. And in the case of a tie, all we're saying is here, we broke ties differently than you broke ties. That's fine. So remember, we did that swap argument. So we're basically saying that the only disagreement you could have is in case of ties. Therefore, our solution must agree with some optimal solution, and therefore reading and returning the shortest book will always minimize the overdue cost, or give us the optimal output for this problem. Okay, so that completes the proof, and actually that's the bulk of the work for this algorithm, is the proof. The coming up with the algorithm, the running the algorithm, the analysis of the algorithm is all very, very straightforward and simple. So it's the proof that was the effort that we need to put in here. And so that's why I focused most of our time and effort on this proof. Now, I want to finish this video here with just a quick look at what we've done in this proof. And I can do that here with this sort of template proof that I've got. Now, this isn't a perfect template, but it's a good way to sort of see the pieces of what we're putting together. Okay. Now so let's go through it one more time and just sort of identify what did we do in that last proof. Well, remember, we started with an arbitrary instance. That ensures that we have a general proof that applies for any possible input we've got. And we want to resist making assumptions about our input unless they preserve our generality. Okay. Next, we needed something to talk about. So I usually use S and O. S for the solution that our algorithm gives us. O for some optimal solution. Now here we want to be as precise as possible about what constitutes a solution. And often we can go to the problem specifications. The output component in particular is going to tell us what a solution looks like. For instance, in this problem, it was a permutation. Okay, here we're sort of looking at what a valid solution might look like, even though down below we might create invalid solutions. We want to start out with valid ones. Okay. The other thing is we're going to want to compare our solutions sort of one at a time. And so there's a piece here in our setup where we need to say, well, what order are we going to compare them in? and usually we want to stick to our order if we can. Now for this problem with the library books, the order is what determined the optimality of the algorithm, and so we can't change the order of the optimal solution. The optimal solution has to be assumed to be in whatever order it's in. However, in other problems, we might have some freedom to mix the optimal solution up into our order, and in those cases we usually say put it in the same order we would have done it, so that we can compare the choices we make to the choices that the optimal solution would make in the exact same situation. Okay. All right, so again, what order should the solutions be presented in? Usually that's, again, stipulated by the problem in some way, but if you're looking for somewhere to look at how your algorithm orders them. That's usually the first advice. Okay. Now we're going to dive into what I call the pseudo-induction here. Okay. The pseudo-induction is where I'm saying, okay, let's assume they agree up till now. That's the pseudo-inductive hypothesis. Assume everything's okay up till now, and then let's only talk about this point where maybe they don't disagree. Okay, and that's some pseudo-induction. And again, we're assuming they don't disagree here, or sorry, don't disagree. I'm double negativing here. I'm assuming they do disagree at this point, point I. For the sake of argument, that argument might arise in a contradiction, meaning no disagreement could have ever arisen. Or we can do that swap argument. Okay, show how we can modify O and still argue that it's valid and optimal. Okay. Now, the contradiction can arise because of a couple different ways. Case 1 arose because it contradicted what we know about our algorithm. We always pick the shortest book. Case 3 was a contradiction because it was a contradiction to our assumption that O had the minimum cost. In this case, that it was optimal. So when you're looking for contradictions for your cases, they can come in sort of one of two ways. One, because it contradicts how your algorithm works. Two, because it contradicts your assumption that O is optimal. And then usually we just finish off with a little postambule here saying, look, so now they don't disagree at this point I. We could do this for any point that they disagree. That's the induction coming back in again. So we'll just conclude that they agree on every point. Now, I will mention, or I did mention earlier, that if you were to look at some of these proof of correctness online, they might not have all of this machinery built in. And in fact, usually what they're going to start doing is they're going to jump right to here, this ball, because usually this is where the creative stuff comes in. But for those of us who are maybe not as mathematically mature, we might not be able to fill in all this extra stuff just easily without sort of understanding how it works. So I'm going to present, at least in my series of videos here, sort of more involved proofs of correctness with this extra machinery around, filling in some of those gaps that get brushed over pretty quickly in a shorter proof of correctness. Okay, so one, if you're looking at my proof of correctness in these videos saying, hey, there's a lot going on there, I've seen other ones that are shorter, I'm filling in some of the pieces that are not there. Two, am I filling in all the pieces? No, not necessarily. You could fill in proofs forever and ever with going all the way down to base principles and get something really, really unwieldy and not really easy to read and understand. So I'm trying to balance here, as any mathematician does, the desire to be communicative to my readers with balancing sort of some assumptions about what my readers already know. Okay, and so again, if you take a look at some of those proofs online, you might just see shorter proofs that are going to be focusing on really on just the meaty chunk in the middle of our proof. Okay. All right, thanks a lot for watching this introduction to greedy algorithms. Stay tuned for my next video where I'm going to take a look at some more greedy algorithms.